Swayam Prabha. Digital India. Educated India.
Now, let us see the fabrication of micropattern for AJMM process, that is abrasive jet micromachining process. In abrasive jet micromachining, the substrate has to be shielded by a wear resistant mask that is patterned with the desired contour, as I mentioned in my earlier lecture on AJMM, that the material is to be removed from the naked surface, because part of the surface, workpiece surface, is covered with the maskant. The mask determines the accuracy of the dimensions in the plane of desired structure, because whatever is the accuracy of the mask, that will be reproduced on the workpiece surface. If mask itself is not accurate, then definitely you are going to get the part which will not be satisfying the requirements of the design. During blasting, the workpiece is exposed to an abrasive air jet, pressure being 0.2 to 0.8 megapascal and abrasive particles average diameter being 10 to 100 micrometer, depending upon the material removal rate that you want. That will decide the pressure of the abrasive jet, and also the accuracy that you want, that will be governed by the diameter of the abrasive particles. So, you have to decide and choose the right kind of the pressure and right kind of the abrasive particles. The scan strategy and the particle beam profile of the nozzle are of great importance. This is the particle beam, abrasive particle beam. The scan strategy and the particle beam profile of the nozzle are of great importance, because particle beam size and shape is going to create a particular type of feature or cavity on the workpiece surface. All process steps are summarized in this particular figure taken from this particular paper. Now, let us see the preheat of substrate. This is the workpiece substrate. It is preheated with the help of this particular heater. Then on this workpiece surface, you are laminating the mask film. This is the mask film which is being laminated, because the workpiece is already heated, though this mask film will get adhered to the workpiece surface. Now, then it is exposed to the lamp. This is, you can see clearly, this is the workpiece surface, this is the workpiece, and this is the mask, and this is the exposure through the lamp. Pattern film, mask film, both are shown over here, and this is the pattern film. If you see here, this particular one, where you can clearly see the circular patterns are made, and then you have the light from the lamp. So, the light through these patterns, circular patterns in this particular case, is given to this particular mask film that is given over here. Then once the mask is exposed to the light through these patterns, then this is developed in an appropriate manner, as you can see over here. Now, then it is rinsed with the help of the water. Water rinsing is there on the developed mask. Then acid neutralization is being done for this particular mask, and then this is the heater which is removing the adhered, if any, water drops or water layers. With the help of heater you can remove them, and then you can see here, this is the nozzle, this is the bottom of the nozzle, and this is the air abrasive jet which is coming and hitting. Now, here this is the mask which is not affected with the by the abrasive particles over here you can see, but this is a workpiece material from which material is being removed and you are getting this particular cavity. So, this is the mask, this is the mask, this is the mask, this is the mask. So, no material is being removed from the mask, but the naked area of the workpiece is subjected to the abrasive particles impacting over there and removing the material and creating this particular cavity on the workpiece surface. So, in this way, using the mask you can create the desired feature on the workpiece surface using abrasive jet micromachining, and definitely it will be in the category of micromachining if your feature size is in microns. So, that means in this particular case you can have the diameter of these features on this particular mask in the micron size, and then if you are using this abrasive jet, then definitely you are micromachining and you are getting the desired pattern over there. But very clearly please see here that this is a kind of tapered surface you are getting in all the cases, and this is due to the characteristics of the abrasive air or abrasive gas jet. Now, which you can see in the book on advanced machining processes, that how this air abrasive jet behaves as it moves away from the workpiece surface, and or you can say as the extent of distance increases, then this becomes different. Now, please note here that in this particular case when you are machining here, this becomes the extent of the distance if you are further machining, and in the beginning this was the extent of distance. So, as I mentioned earlier, extent of distance or nozzle tip distance keep on changing. Now, let us see the masking technology. The quality of the masks influences the performance of abrasive jet micromachining. As I showed you in the earlier transparency, let me show it. Because of these abrasive particles, if the mask is burned out over here, then definitely machining will take place here also, and you will not get the feature of the desired characteristic. That is why it is important that mask is resistant to the abrasive particle. And then you can say the main qualification for a good mask material is a low erosion rate. That means material removal or maskant removal should be quite low, so that the workpiece surface is not exposed to the air abrasive jet or air abrasive beam. It also requires the capability of an accurate and easy pattern transfer and the ability to retain their resistance in discontinuous layer, because if the maskant you cannot create the desired pattern, then it is of no use. So, it should not be too hard to create the pattern. Three groups of mask materials can be applied to abrasive jet micromachining. As you can see here, you can have ductile materials just like metals, you can have elastic materials such as elastomers, and you can have photoresist material as used in IC industries. Each type of these mask material needs a sufficient erosion resistance, a certain minimum erosion resistance related to the substrate, especially at normal blast angle. So, erosion resistance is the one of the main characteristics of the mask. Then furthermore, the achievable imaging accuracy determines the usability of a mask and minimum achievable feature size. So, depending upon how accurately, how small or what small feature you can create on the mask, the same will be reproduced on the workpiece surface. You can use the metal mask as mentioned in the earlier slide. Ductile materials like metals have a low erosion rate, especially at perpendicular angle. When you are having the 0 degree angle, that means here is the workpiece surface, abrasive jet is coming over here, then this makes them suitable to be used as a mask material. It can be used by means of a thin plate. You can have a stainless steel plate as the mask material. Micropattern can be created by micro drilling, micro milling of laser machining in this particular type, especially in case of metal masks. By other methods also, by advanced machining processes also, you can create the micro features in the metal mask, and that can be used for creating further features with the help of abrasive jet micromachining. To apply this mask plate for AJMM, it can be magnetically clamped directly to the target or by introducing an intermediate protection or addition layer. So, you can clamp the mask on the workpiece surface for abrasive jet micromachining, or you can have a adhesive layer between the mask and the workpiece to put it on the workpiece surface before you really start the abrasive jet micromachining, something like this. You can have the workpiece surface, you can have the mask here, and this mask is having the adhesive layer. You put it inside this, so this will get adhered over here, and then you can do the abrasive jet micromachining. A relatively thick metal layer lasts for a long time. So, a mask can be used on several targets. It simply means that you can reuse the same mask for many workpieces rather than one single workpiece if the thickness of the mask lasts for a long, that means it is quite thick. So, it depends upon your requirement, mask material and other things. Another thing is the disadvantages of this mask, that is metal type mask, are the limitations in feature size, because on the metal mask you cannot create very fine features, just like few tens of micrometer features, 10 micrometer features or less than that are comparatively difficult to create on the metal mask, and pattern constraints are there, just like you can create circular pattern cannot be used because the inside should be supported. In these masks it says that circular patterns cannot be used because the inside surface should be protected. So, there are certain constraints, certain disadvantages in each type of the mask, as we will see. So, metal mask, how to do it? Let us see the process. This figure indicates the whole process, I will explain it. In order to combine the low erosion rate of a metal and the high resolution of a lithographic process, a metal mask can be applied on the target by electroplating. Electroplating process, as we already know, is the deposition of the material on the metallic workpieces. So, with the help of this electroplating you can use the resolution of lithographic process, you can use this process for creating the features on the metallic mask. Copper is used by this method, while zinc mask can be made by electroforming. Another process, electroforming, can also be used. The whole target is covered by titanium, 15 nanometer copper, 400 nanometers seed layer by sputtering. Now, you can see here either titanium or copper seed layer is produced over here as shown in this particular figure 1, portion 1, and this is in the red color. After that, in order to combine the low erosion rate of a metal and the high resolution of a lithographic process, a metal mask can be applied on the target by electroplating, as we have just seen over here. It works as an intermediate addition layer between the target and the copper. Electroplating, that works as the intermediate addition layer. Now, second step, that is this one, a thick polymer foil that is commonly used with electroplating is applied as a mold in which the copper is grown. This is the mold shown over here, this is the metal mask. A third step, micropattern is lithographically defined, as you can see in this particular case, that here pattern is created over there, and fourth, now the target is plated with copper. Red color you can see that the target has been plated with the copper, and that is shown over here in the red color. Now, after which in the 5 step that you can see here, after which the polymer is removed with 10% KOH solution at room temperature. So, the polymer has been removed, that is blue color over here, it has been removed, only red color is left over there, which is showing the feature. And 6, the thin seed layer beneath the resist mold is generally not removed separately, but is easily etched away during the blasting. So, you can see that layer is not removed over here, and you have these features over here. Then you apply the abrasive jet machining over here, 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 because here you have already the mask. So, abrasive jet particles will not work over there, but in these cavities abrasive particles will cut the material, as you can see clearly over here. The cavity is being formed over here with the help of the abrasive jet. This is the abrasive air jet. So, you will be able to create the cavity in the area where there is no mask. After blasting, the remaining copper can be removed with a strong acid. After blasting is over, then this copper layer that is shown by red color, it can be removed with the strong acid such as nitric acid HNO3 or other suitable acid can be used depending upon what is the material of this metal mask over here, just like the one shown over here. Now, other than metal mask, you also have elastomer mask. The erosion mechanism of rubber like materials differs essentially from that of brittle materials or ductile materials. We have already seen metal mask. Now, no lateral cracks are formed in elastomers as found in brittle materials. As I have mentioned in the earlier lecture, that when you continuously keep hammering the workpiece surface or the mask with the help of the abrasive particle at normal angle, then that metal becomes hardened because of strain hardening, and there lateral cracks may be created. But in case of elastomers, no lateral cracks are formed in elastomers as found in brittle materials, neither do any evidence of cutting or ploughing where as found in metals. So, no ploughing, no cutting takes place in case of elastomer mask. Since the erosion mechanism of this class of materials is based on fatigue, they display a good erosion resistance. Elastomers, they give a good erosion resistance. The photoresist sensitive materials can be patterned accurately using lithography. Photosensitive elastomer can be a good option for the mask. However, in contrast to ductile or brittle materials, elastomers behavior is dependent on temperature, rate of deformation and particle velocity. So, you have to control the temperature, otherwise elastomer properties will change, and the rate of deformation and particle velocity, both of them will affect the behavior of the elastomer as a mask. So, this has to be taken care of. Thus, elastomers can show ductile, elastic and brittle behavior, and experiments have to be carried out under relevant practical conditions. So, that elastomer does not change its shape and size, otherwise the feature that you are creating will also change its shape and size, which is not desirable. These types of masks, usually these types of masks, as is the machine, these types of masks usually provide in the form of ready-made foil with self adhesive properties. These are the ready-made foils are there, which have adhesive on one side of the foil, and you put it on the workpiece and it will get adhered to the workpiece surface. Photoresist mask. Third type of mask is photoresist mask. Photoresists are photosensitive material. They are very important and they are used for very fine feature creation, especially in case of lithography and other kind of the processes. There are two types of photoresist, positive and negative. For positive photoresist, the resist is exposed with ultraviolet light wherever the underlying material is to be removed. From wherever you want to remove the material, on that particular part the ultraviolet light should fall on photoresist mask. In these resist, exposure to the ultraviolet light changes the chemical structure of the resist, so that it becomes more soluble in the developer. When this resist is put in the developer, then wherever the light has fallen, ultraviolet light has fallen on the photoresist mask, that part gets dissolved and you are able to create a mask with desired pattern. And when it is subjected for abrasive jet micromachining, then you are removing the material from the area where from the mask has been removed. So, the exposed resist is then washed away by the developer solution, leaving windows of the bare underlying material. So, wherever you have bare underlying material or naked material or material with no mask, from there only the abrasive jet removes the material. In other words, whatever shows goes. So, whatever is shown over the workpiece surface through the mask, that material gets removed when abrasive jet impacts on it. That is why it says whatever shows that goes. The mask therefore contains an exact copy of the pattern which is to remain on the wafer. So, whatever is the pattern to be created on the wafer, that should be accurately reflected on the mask, otherwise your product will get rejected if it is not having proper characteristics. Negative resists behave in just the opposite manner, right. So, that means wherever light is not falling, that part will get dissolved in the developer and then rest of the process will remain the same. Epoxy based SU8 is one of the good negative resists. It is able to provide features with high aspect ratio, that is greater than 10 with ultraviolet lithography break. Now, let us compare the masks. Metal masks made of stainless steel masks are very suitable for high particle velocities and fast machining operations. Whenever you have high particle velocities, their kinetic energy will be high and they can erode the mask itself. But since it is made up of stainless steel, so the erosion rate will be very low and it will not affect the shape and size of the mask, which is going to govern the shape and size of the feature or the pattern created on the workpiece surface. Structure with high aspect ratio are achievable due to the low erosion rate of steel. That means high aspect ratio, that means depth upon diameter, that you can have very high aspect ratio in case of metal mask, because you are using high velocity of the particle, and because of high velocity of the particle, even then the mask will not get eroded substantially and you can get accurate pattern generation on the workpiece. Attention has been paid to the adhesive layer, which should not only stick the two materials together, but also avoid under etching. So, because as we have not discussed here, but if you see in other processes under etching takes place, and because of that under etching you get larger overcut. That means, if you are having the D as the diameter on the pattern, then you will get D plus delta D, and this delta D is known as undercut, as I can show you here. This is the one you require, and here is the mask, and you are putting this here, then this cutting will take place here also, because abrasive particles after reflection will remove the material from here and here, and this undercut affects the final dimensions of the workpiece. So, you can avoid this. The limiting factors for all metal mass are the feature width and the structuring procedure where no free standing contours are possible. The metal mass should be applied preferably for medium and large sizes, because very small sizes it will be difficult to create the pattern on the metal mass. That is why it is recommended that for medium and large sizes you should use the metal mass, while for small sizes you should think of using other types of mask. Now, there are other types of mask, elastomer mask, as we have already seen. Elastomer foils are easy to pattern and allow a high complexity of the design, but the procedure is somewhat time consuming. In elastomer, you can create complicated shapes on the pattern, which will be reproduced on the actual workpiece, which are difficult to produce on the metal mass. Hence, from that point of view, elastomer foils or elastomer masks are more suited for complex shaped workpieces. They are not suitable for high air pressure, because at high air pressure elastomer itself will get eroded and de-shaped, and as a result of that your feature creation will be affected with reference to dimensions and shape or geometry due to their elastic deformation behavior. So, one has to be careful while using elastomer that pressure, air pressure or air abrasive jet pressure should be low, otherwise elastomer mask will not work as expected. The adhesion is significantly weaker for complex patterns and higher particle velocities that may cause release of the foils from the substrate. Release of the foil from the substrate should not take place, otherwise your whole workpiece may get spoiled or damaged. That is the preliminary requirement, and so adhesion should be done very carefully and strongly, and their applicability is limited to single workpiece and feature size down to 75 micrometer. This is very important, as we have seen in case of metal mask. You can recycle the mask, you can reuse and reuse the mask till it gets eroded substantially or eroded to the extent that it is going to affect your feature creation on the workpiece. But elastomer masks are normally used once only, and then they have to be changed, and the feature sizes that you can create is down to 75 micrometer. Then there is a photoresist mask. A good compromise in terms of feature size and imaging accuracy gives the epoxy based photoresist, and one of them is SU8, and a drawback is the expensive equipment to prepare the mask and its low selectivity. So, equipments are quite expensive to prepare the mask. Now, a good compromise in terms of feature size and imaging accuracy gives the epoxy based photoresist SU8. A drawback is the expensive equipment that I have already mentioned to you. Since the maximum thickness of a SU8 layer is about 300 micrometer, so no high aspect ratio is achievable. So, you cannot get very high aspect ratio as in case of other mass, and its application is limited to shallow cavities. So, for shallow cavities this photoresist is quite good. For other categories you have the metal mask and elastomer mask. Now, another important parameter or aspect of this particular abrasive jet micromachining is abrasive powder feeding. One of the major difficulties with the abrasive jet micromachining process is the handling of very fine abrasive particles, because abrasive particles have to be very fine and in the range of micro nano sizes, because you have to mix these abrasive particles with the air as homogeneous as possible, so that you get good quality feature creation on the workpiece. For this purpose, powder flowability and compatibility are greatly influenced by particle size, size distribution, moisture content and surface texture. Now, here particle size, if it is larger particle size, then you will not get homogeneous mixture of the air abrasive particles. Size distribution is also very important, because if you have say 10 micron size abrasive particle, all abrasive particles are not going to be of 10 micron size, they may be having the normal distribution something like this, where this is the particle size and this is the distribution size and distribution. So, this is very important to understand that size distribution should be proper, otherwise your feature characteristics obtained on the workpiece may not be the one that you are looking for. And then moisture content is another aspect. Moisture content should be completely removed from the air abrasive particle mixture, because if moisture content is there, then abrasive particle will get agglomerated and you will not have uniform distribution of abrasive particles in the air abrasive jet, and that will not create the desired feature characteristics. And the surface texture of abrasive particle is also important, as I have mentioned in the earlier slide. It is always desirable to have sharp abrasive particles, because if abrasive particles are sharp, then their cutting capability or machining capabilities are better than other size of the other shape of the abrasive particles. Another thing is interparticle addition is further enhanced by moisture. That is what I have mentioned, that adsorbs readily onto the hygroscopic surfaces, having a tendency to absorb moisture, and once they absorb the moisture, they adhere, agglomerate, and then it is not going to work properly. Also, another danger is that if moisture is there, they will agglomerate, and when they are coming through the nozzle, they may even break the nozzle, and as a result of that, whole process has to be stopped and you have to replace the nozzle by the new one. And these nozzles are very expensive, because they are made of the material just like tungsten carbide or sapphire, which are very costly materials. Then you have consequently the relative humidity of stored air can have a major influence on the adhesive forces at the interface of particles, and I have already shown to you when I was discussing the equipment or setup of abrasive jet micromachining, that heater are used to take away the moisture from the abrasive particles, so that these kind of problems do not arise during mixing and use of the abrasive air jet. Another point is, furthermore, it is well known that the movement of powder leads quickly to stratification and the creation of gradient of particle size and or shape. So, this to avoid such kind of problems, humidity should be minimized, or there should be no humidity left, and particle size distribution also should have as narrow as possible, means the particle size should be more or less of the same size. Now, such problems result in alteration of the powder mass flow rate, because powder mass flow rate has significant effect on the performance of the process. So, such problems result in alteration of the powder mass flow rate during the course of abrasive jet micromachining experiments, especially when moisture is there. This problem may happen very commonly. So, what is hydrophobic surfaces? That is very important. I will tell you having no affinity for water. Hydrophobic surfaces, as you know, the surface of the lotus flower. If you put a drop of water, it will not stay on the leaf of the lotus, because its surface is hydrophobic. So, texture on the metallic surfaces or not metallic surfaces can be created which are hydrophobic in nature, and such creation of such kind of surfaces it really difficult. Then powder feeding control, the way you are feeding the powder to the mixing tube or and then later on it goes to the nozzle is very important, because I have been emphasizing on homogeneity of mixture of the powder and the air. So, powder feed control of two microblasting systems is considered into two types. One is the pressurized powder feed system, another is the fluidized bed powder spray system. Both systems have their own merits and demerits. We will see both of them one by one. Other approaches to the control of powder mass flow rate include vibratory and screw or auger feeding, in which the powder is fed to the conveying air through an auger, similar to the tool used for boring earth. And then introducing a vibrator to a screw system improved the steadiness of the powder feed, and finally, but the improvement diminished with fine more cohesive materials such as zeolite and cement powder due to phenomena such as powder bridging, compaction and agglomeration. So, you can see here also that agglomeration is one of the big problem, and this is enhanced in the presence of water or humidity or water vapor. That is why removal of the water vapor or drying of the air is very important to get good performance in abrasive jet micromachining. Pressurized powder feed system, I will show you. The powder is fed to the air stream from a pressurized reservoir through an orifice and mixing chamber. The system utilizes an oscillating valve that splits the operation cycle into two halves. The operation cycle is activated by a switch only after the entire system including reservoir has initially been pressurized by closing the nozzle and opening the oscillating valve to the main air supply. So, you can see here the details of this particular system. You can see here this is the orifice bypass, high pressure air is being supplied from here, and you have the oscillating valve over here. This is the mixing chamber, and from here this will be going, this powder is from here coming over here, this is getting mixed up in the mixing chamber because air is coming from this side, powder is coming from this side, both of them getting mixed up in this mixing chamber and passing towards the nozzle. Here nozzle valve is there, you can open the nozzle valve, then this will go out. If you close this nozzle valve, this air abrasive mixture will not go out, and you can see here orifice is there, powder tank is there, powder is there, and up to this level it is filled up. So, during the first half of the operation cycle, the oscillating valve is open, allowing air to flow from oscillating pressure air, high pressure air. This is the oscillating valve, when this is opened it comes over here. While some enters the powder reservoir and the rest flows out through the open nozzle. This is the nozzle. If it is open, it will go out, if not, then it will remain over here only. Pressurized powder flow system continues. It is during this first half cycle that any powder that has entered the mixing chamber is forced out of the nozzle. This is the mixing chamber. Whatever powder has entered from this into this, it will be forced to go out through the nozzle. In the second half of the cycle, the oscillating valve is closed, stopping airflow through the system. So, this oscillating valve is closed and airflow is stopped to the mixing chamber. Then at this point the reservoir is still pressurized, but the mixing chamber is at atmospheric pressure due to the open nozzle. So, this is the mixing chamber. So, this creates a pressure differential that forces the powder down through the orifice at the bottom of the reservoir and into the mixing chamber. So, from here, once this is stopped, powder comes from here through this and it enters into the mixing chamber, because you have closed this. So, because of the differential of pressure here as well as here, you get this powder into the mixing chamber. The oscillating valve then opens. Once this powder has come in the mixing chamber, then automatically the oscillating valve is opened, then air comes in. Limited control of the powder mass flow rate is possible by regulating the air flow rate through the reservoir by changing the orifice bypass, and then both of them, air as well as the powder, they get mixed up in the mixing chamber. The size of the reservoir orifice also controls what will be the flow rate of the powder.